in this component of your book, they're talking about what it means for a graph to be symmetric over the x-axis, what it means for the graph to be symmetric over the y-axis, what it means for it to be symmetric over the origin. And then in example 5, again, we're looking at the graph first to draw any conclusions about symmetry, and then we're supporting that algebraically and numerically. All right, so part A, looking at the graph, I would hope that you'd think, well, it looks like there might be some symmetry over that line, which is my y-axis. So for part A, first thing to address is whether it's symmetrical over the x-axis, y-axis, or origin, and we're going to say it's symmetrical over the y-axis. And then it wants us to support that numerically, and what they mean by that is take an x value, plug it in, and then compare it to the negative of that x value. So here's what I mean. Let's say I plug in x equals 1. If x equals 1, then what does y equal? Y would equal -1 plus 6, which is 5. If I plug in -1, if this is truly symmetrical over the y-axis, then y will also equal 5. So if I plug in -1, -1 squared is +1, but I still have a negative sign there, so now it's back to -1 plus 6 is 5. So y does equal 5. But you don't just want to do it for one pair of numbers. You want to make sure you try it for at least 2. So let's try x equals 2. If x equals 2, what does y equal? Well, 2 squared is 4, and then I'd have -4 plus 6 equals 2. And again, if this is truly symmetrical over the y-axis, then plugging in -2 will also yield 2 for y. So let's do that. If I take -2 and square it, it's +4 again. But I've got that negative sign out front, so it's -4. And then plus 6 is 2. So I have supported that answer numerically, and then it wants me to confirm it algebraically. And what that means is my f of x, remember, was -x squared plus 6. If it's symmetrical over the y-axis, then replacing x with -x will give me the same exact equation. So let's work that out. Okay, so if I have -x and I square it, it becomes x squared. I've still got this negative sign in front of it, plus 6. It's an equivalent equation. So I have just confirmed this algebraically. I'm getting ready to erase this screen, so if you don't have it yet, you might want to pause it. Part B. First part of the instructions are to test it for symmetry over the x-axis, y-axis, and the origin. And looks like it's symmetrical over the y-axis. Looks like it's symmetrical over the x-axis as well. And it looks like it is even symmetrical over the origin. So we're going to say it has all symmetry. Right? So that's the first thing that they were asking us, is just to look at the graph for the symmetry. Second thing they're asking us to do is support our answer numerically. So if I replace my y with negative y and I get the same equation, then that covers it being symmetrical over the x-axis. If I replace a value with its opposite as far as the x's, and I end up with the same value, then it's symmetrical over the y-axis. So let's do one thing at a time, and then we'll look at the symmetry over the origin. All right, so if I plug in x equals 3, so if x equals 3, then what does y equal? Well, 3 squared is 9. I would subtract the 9 from the 25 and get 16. So y would equal positive or negative 4. And at 3, if I plug in negative 3, if this is symmetrical over the y-axis, then I should still end up with y equals positive or negative 4. Okay, so if I plug in negative 3 into my equation, well, negative 3 quantity squared is 9. Again, subtract that from 25, I get 16. Y squared equals 16 means that y equals, again, positive or negative 4. In the interest of time, I'm just going to use 1 point to verify numerically symmetry over the y-axis. I'm going to use another number to show it over the x-axis, and then move on from there. Okay, so this has confirmed y symmetry. If I plug in x equals 4, actually, let me go backwards, because now I'm verifying symmetry over the x-axis. So if I plug in a value for y, let's say 3, what does x equal? If I plug in y equals 3, y squared is 9, subtracted from 25 I get 16, x squared this time equals 16, so x would equal positive or negative 4. And if I plug in negative 3, and this is truly symmetrical over the x-axis, then x will equal positive or negative 4 again. So negative 3 squared is 9, 25 minus 9 is 16. Square root of x squared equals 16 means that x equals, sure enough, positive or negative 4. And we have just shown this x symmetry. And then finally, if I replace both x and negative x and y with negative y, I end up with an equivalent equation. Okay, so if I have that x equals 3 and y equals 4, we already know that that is a point in our graph. And when I do that, it's true. And when I plug in negative 3 and negative 4, it's the exact same graph. It's the exact same validity. And then I could go through and confirm all of this algebraically. If I plug in negative x, I would end up with the same equation. If I plug in negative y, I would end up with the same equation. And if I plug in negative x and a negative y, once again, same exact equation. So it can be confirmed algebraically. Finally, this last bit in your text is taking that symmetry to another level and giving it kind of another way to describe it using vocabulary. If it is symmetric over the y-axis, then we say that it is an even function. If it is an odd function, then we say that it's symmetrical over the origin. All right, so notice in these instructions, they're asking you to start with the graph in order to determine whether it's even, odd, or neither. And then they want you, again, to confirm it algebraically. So if you don't have a graphing calculator, remember that you can use Desmos. So the first graph that they wanted us to look at was 2 over x squared. And looking at this graph, I would hope that you would notice that it looks like it's symmetrical over the y-axis. And if it's symmetrical over the y-axis, remember that means it's even. They want us to confirm that algebraically, of course. Well, remember what that means. If I take y equals 2 over negative x squared, I should end up with the exact same equation. Well, negative x, quantity squared, is just x squared. That 2 I'm not doing anything to, so yes, it is the same equation. And it's asking if it's odd or even to describe the symmetry of the graph of the function. It is symmetrical over the y-axis. When we graph y equals 4 times the square root of x, you would notice that there's no symmetry over the y-axis, and there's nothing at all going on in that third quadrant, which is where something should be happening if this was symmetrical over the origin. This is neither as far as even or odd. Confirming algebraically. If I plug in negative x, this does not equal the same thing as 4 times the square root of x. I could be taking the square root of a negative number now, and you know that's not allowed. Okay, so that's not equivalent. And it also doesn't equal the opposite of 4 times the square root of x. For part C, again, looking at that graph, minus 2x. Okay, so I've got my graph, and it looks like it could be odd. I'd hope that you'd notice it's definitely not even. It's not symmetrical over the y-axis, but it could be symmetrical over the origin. Okay, so let's check that algebraically. So I'm going to write down odd with a question mark because I haven't verified it algebraically yet. So if I plug in negative x for x, in order for it to be odd, I should end up with the exact opposite of my original function. Okay, so let's check that out. So when I take that negative x to the 5th power now, I have negative x to the 5th. When I take this negative x to the 3rd power, I have negative x to the 3rd being multiplied by negative 2, so that's plus 2x to the 3rd. And this is minus x. And since this function is the opposite of the original, then it is odd. Oh, it's not F, it's H. Meaning it is symmetrical